So they've moved on to a technique called synchronous rectification. And that's what this machine does on its output, is it uses synchronous rectification in kind of a different way. Normally, synchronous rectification is only done, it's by using a MOSFET. Do we have an eraser? Do I just have to use my hands, or do we have like an eraser up here? Okay, thanks. I'll go for it. Oh, they call it dry erase, so I'll see if they're right. All right. Here's your conventional MOSFET symbol, at least the way that I draw it. It's not a transistor. You see that this looks like a capacitor symbol, doesn't it? And that's because the way that the silicon is made is it has little tiny holes where there aren't any electrons. There's no ability to carry current there. There's hollow spaces. You need electrons to conduct something, and this is hollow there, right? And so they put a little layer of metal oxide here, and when you want to turn this MOSFET on, you charge this positive with respect to the source terminal. You charge it like 10 volts positive. So what you've done here is a positive voltage is withdrawing electrons. So you've made little holes here. The charge always wants to balance, so that means that some electrons through the source leak into here to try to balance out the electric charge. You just sucked some electrons away, so more are going to want to flow in to fill the void. Well, they get into the holes. They filled the holes. Now we have a conductor. Cool! MOSFET conducts. That's great. So by changing the voltage here on the gate and changing the electric field here, we either pump electrons in or out of these holes, and that causes the MOSFET to be an insulator when there's just holes, or a conductor when those holes are filled. Then the electrons can hop between the holes and they carry a current. That's N channel. Well, stay with sort of the theme here, right? Okay. Unfortunately, there's a part of a MOSFET that we don't draw that gets in the way sometimes and is also a wonderful advantage sometimes. So I'll try to expand to that here. That's right, there's a body diode. It's actually a Zener diode. So if we draw the full symbol for a MOSFET that you sometimes see on data sheets and so forth, they will illustrate this diode for you. So if we have a diode that or a MOSFET that handles up to like 1.2 kilovolts, which is what the MOSFETs in here do, that's what they're rated for. They can take positive 1.2 kilovolts with respect to the source. This is the drain. Here's the source. Until that Zener diode starts to avalanche. Then it starts to conduct, and it gets hot. They can easily burn the MOSFET out because 1 amp at a 1200 volt drop is 1200 watts, right? So normally we don't have a MOSFET avalanche. We don't want to do that because it just creates heat. It wastes energy. And if this source terminal goes positive with respect to the drain, positive meaning conventional current, right? We forward bias that diode. So a MOSFET, even though it makes a great insulator when it's off and a great conductor when it's on, that's only with respect to one direction of current flow. In the opposite direction, it's a conventional diode, and actually worse most of the time than a conventional diode. It's a really lousy diode. It's got terrible turn-on time and horrible, it's a crappy diode. Normally because they don't try to optimize the properties of that diode. To do so, de-optimizes the rest of the MOSFET. So they call it a parasitic diode. It's a diode you don't really want, but it's baked into the structure of MOSFET. To my knowledge, there's no other structure out there that eliminates that parasitic diode. So MOSFETs are always one-way devices, which is why we draw this arrow. The nice thing about a MOSFET, though, is it's still a MOSFET in that reverse direction. So if we do put current flow in the opposite direction, we have that diode, and it's going to waste a volt. So we might put 5 volts in and only get 4 out. And that volt of loss times the current through it is the power that's heating up the MOSFET. But if we charge the gate positive with respect to the gate again, or sorry, with respect to the source, it's still a MOSFET. It still turns on. It shorts out that diode. Now it's like a perfect conductor again. So what a synchronous rectifier does in order to save power, and this is in your laptop or any computer these days, is we have like a coil or something like this with a MOSFET instead of a diode. Let's say that we want a negative voltage out here. So when this coil induces a positive voltage, we treat that as the diode off. We gate the MOSFET off, it doesn't conduct, and it blocks. But when there's a negative voltage here, if the MOSFET were on, we'd see that diode, right? But instead, we turn the MOSFET on. Now it's shorted out. Bingo. No drop. That's why they call it synchronous rectification. The MOSFET has to be turned on and off synchronously with the AC polarity coming out of our secondary coil. And if it's done, and if it's done well, the only losses are the DC resistance of the MOSFET in the coil, which can be very low. That's why you don't see heat sinks on these things. It's also, if you look at this, if you look at the output MOSFETs, they're just hanging there. I don't heat sink them. I don't have to. They don't get hot. So let's look at the signal across those output MOSFETs. And I'll have you know, this is the part that I wasn't going to show you. This is the secret of the device, because it's the one thing that I do that seems to make the whole thing tick. And when I was still in fear mode, and I said, holy smokes, this thing works. Maybe I'll just tell Aaron I'm not going to go to the conference. You feel me? There was that human nature thing. And I said, what? This was my personal experience. I saw in myself the same thing that I have bemoaned in other inventors who got in their own way and chose to hide what they had created for fear of loss. And I said, I wasn't shown that for a decade straight just so I could be liable of the same thing, so I have to give it away. And this isn't the best thing I've seen. This is just the only one I've created. So you got to give it away. Otherwise, you're a schmuck.